we talked about the pH and what that meant, how to find the pH of an acid solution. So we're going to dig into that a little deeper. There are two possible sources of hydronium ions in a solution that has an acid in it. We've got the ionization of the acid itself, but we also have the autoionization of water. Most of the time we can ignore that, but if we have an extremely dilute acid solution, meaning lying down around 10 to the minus 5, then we can't ignore that anymore. So strong acids, again, by definition, ionize completely in water. So finding pHs of strong acids is easy. So the concentration of hydronium ion in a strong acid solution is just equal to the concentration of the strong acid. And this is what we assumed everything did in Chem 1A. So if we have a 0.1 molar HCl solution, then the hydronium ion concentration is going to be the same number, 0.10 molar, right? And then if you take the negative log of that, we get a pH of 1. Any questions about that? Weak acids, which, all but 6 of them are weak acids. Here, we have an equilibrium problem to solve because the weak acid only ionizes partially. And so here come the ice tables again. So the initial hydronium ion concentration is not 0, but we write it's approximately 0 because it would be 10 to the minus 7, which most of the time is small enough that it doesn't matter. So this is not written as an equation, but let's see if I can make it look like one. And then we would have, it's a little bit fat. So we've got our weak acid and water, and the weak acid donates its hydrogen ion to H3O, giving us H3O plus and A minus as the product. So for initial concentrations, hydronium ion initially is approximately 0. The conjugate base is 0, and we put in the acid concentration here. So, it says 0.1 molar acetic acid on the bottle. Well, that's what we put down as our initial concentration. And then we need to do an ice table to figure out, well, how much of that ionizes and what actually is the pH. So then we've got the change, minus x, and plus x, and then we add initial and change together to get equilibrium. And then we can take these expressions and plug them into the equilibrium constant expression and figure out what x is. And so this is the approach for finding the pH, or the hydronium ion concentration, for a weak acid. It's what we learned how to do in chapter 16. So let's do it. Find the hydronium ion concentration of a 0.250 molar hydrofluoric acid solution. And they're giving us the acid ionization constant because nobody remembers those things. So I like to start by writing a chemical equation describing this. And with a simple one like this, we can just use the actual formula, HF. And so that's going to be in equilibrium with H plus and F minus. And this is where I find it more convenient to use H plus instead of hydronium. If we want to use hydronium, then we have to add water over here. And then we can have H3O plus in there. So since I already added that in, we'll leave it here this time, but in the future I'll most likely leave it out. That's a good color with red, I guess blue. Okay, so we're gonna make an ice table. Do we need to keep track of the H2O concentration? No, we don't. So it's sitting up there and actually just kind of getting in the way, and that's why I usually just leave it off. So we have our initial row, our change row, and our equilibrium row. So this concentration they give us for this weak acid, 0.250 molar, that's what we put in as the initial concentration for the acid molecule. So that's 0.250. And what's the initial concentration of hydronium? Approximately 0. And how about fluoride ion? That's going to be 0. Okay, so then we look at the change. Well, HF is going to lose X amount. H3O plus is going to gain X, and F minus is going to gain X. Then we're going to add our rows together. 0.250 minus X, 0 plus X, and 0 plus X. So the equilibrium constant here is called Ka, and it's going to be the hydronium ion concentration times the fluoride ion concentration divided by the hydrofluoric acid concentration. So we are told that Ka is 3.5 times 10 to the minus 4. And so that's going to be our two products. They are each X, so I'm going to write X squared. And it'll be divided by 0.250 minus X. Everybody see how this is going? We had two choices here. We could try the X's small approximation, or we could use the solver. This is a fairly good-sized concentration here. It's a small Ka, but it's not especially small. So I'm just going to go ahead and use the solver. And if anybody needs a calculator, they are over here. This is another chapter full of ice tables. So I'm going to plug this into my solver. 3.5 times 10 to the minus 4 on the left. On the right, make a fraction. We got X squared on top. And 0.25 minus X on the bottom. So I'm getting X to be 0.009181. Anybody else confirm that? Thank you. So that is then, X is the concentration of hydronium, which is what we're trying to find. So the hydronium ion concentration, and we can write that in decimal form. I'd probably go with 2 sig figs, 0.00 0.092 molar, or we could express that in scientific notation, 9.2 times 10 to the minus 3 molar. Any questions? If you're still iffy on ice tables, today is the day to get it figured out. Yeah?
I got the same thing you did on the slide. It's 0.013.
Say that again?
I got the same thing that you did on the slide. It says 0.0.
Oh, okay. Yes, it does. 0.013. Okay, let's see if we can figure out what happened. So I'm checking the textbook, which is where I get all these problems, and they've got 9.4 times 10 to the minus 3. So that's what I got with the x is small approximation. So my slide has a mistake on it. Nice. This question is asking us to find the pH of a weak acid solution. So here we have acetic acid, 0.015 molar, and here is its Ka. We're going to need an ice table again. Bless you. So acetic acid is HC2, H3O2. And so we can use that in our little equation, or we can call it HA. Right? So then the anion here, the conjugate base, acetate ion, is A minus. And so we'll see that we tend to do that a lot because it just speeds things up. Because do we really care about the formula for the acetic acid? No, not in this kind of a problem. So I'm just going to use that simplified equation. So we've got HA representing our acid in equilibrium with hydrogen ions that we understand are not out by themselves. They are on water as a hydronium ion. And then we make our ice table. ICE. So what's the concentration of our weak acid? 0.0150. What's our initial concentration of hydrogen ion? Approximately 0. And of the acetate ion? Also 0. And so then we're going to have minus x, because that one can only go, that one's going down, and these, because these can only go up. And then we'll add them together, 0.0150 minus x, x, and x. So Ka is equal to the hydrogen ion concentration times the acetate ion concentration divided by the acetic acid concentration. So 1.8 times 10 to the minus 5 is equal to x squared divided by 0.0150 minus x. So on the last one, I did a quick calculation at the end, and it was x was 3.7%. So we could have used the x is small, and I believe that's where the book got its answer. Here, our starting concentration is smaller, And so I'm pretty sure x is small is not going to work. So I go back to the solver. .8 times 10 to the minus 5 x squared 0.015 minus x. X is 0.0005107. Yeah. That's 3.4%. X is small woodwork. Let's do X is small here, just as a review. So when we say X is small, what we're doing is we're saying that this is so small relative to this number that it's being subtracted from that we can just ignore it. It's like the peach that fell off the big truck, right? It really doesn't matter. It's not going to change the mass noticeably. So that goes to 0. And then we can rearrange that and we get x is equal to the square root of 1.8 times 10 to the minus 5 times 0.015. And so the approximation there gives us 0.0005196. Those are really close, right? So X is the hydrogen ion concentration. Is this the answer to the question? No, they want the pH. So if we use the solver, we've got 0.0005107. And the pH comes out to be 3.918. Based on the equilibrium constant, I'd probably call that at 2 sig figs. And so the pH would have 2 decimal places. And now I'm just going to do that also with the X is small version, to see what kind of a difference it makes in the pH. .2843. 3.28. So we have a difference of 1 in the uncertain digit. Is that a problem? No. Any questions? .28. Okay, so this one is telling us that X is small doesn't work. So, we already inadvertently practiced doing that on the last 2 problems. It's okay. So here we've got HNO2. Do you want to use HNO2 or do you want to use HA? Anybody care? You'd rather have HNO2? Okay. Let's do HNO2. HNO2 in equilibrium with H plus and NO2 minus. Everybody okay with me using H plus here instead of H3O plus? It just makes things shorter. I'm realizing that that is way off to the side, so I'll move that guy over. And another ice table. ICE. Okay. Initial concentration for the acid? 0.010. This is the molarity that they give us. Initial concentration for hydrogen and nitrite? We'll call this one approximately 0 because it's not actually 0 and I can't bring myself to write 0, but it's close enough. And so the change then ends up being just minus x and plus x. So 0.010 minus x and x and x. Okay, A. We seem to be doing just the same thing over and over again, right? We are. But we are going to throw twists into it real soon. Now we're going to plug everything in. 4.6 times 10 to the minus 4 is equal to x squared divided by 0.010 minus x. I'm just going to run the x is small really quick so we can compare it. It's going to be the square root of 4.6 times 10 to the minus 4 times 0.01 0.002145. That is 21% of this number. So we can't ignore x when we're subtracting here. So we do need to use the solver this time, or, God forbid, the quadratic equation. 4.6 times 10 minus 4. So the solver is giving me x is equal to 0.001927. It's not crazy different than the approximation, but there's definitely a bigger difference. And so that's our hydrogen ion concentration. It's also the nitrite ion concentration, but that's not very useful. So pH is the negative log 0.001927. can just hit negative log, and then if I hit that variable button, X, and hit enter, it remembers the X that I solved for. And so the pH here, 2.7151, and again, this should have 2 sig figs, so 2.72. Any questions? Yeah.
So when do you assume that x becomes to go to 0?
When do you assume that X is small? That is an excellent question. And there's not a perfect answer to that. So one of the earlier examples, I was thinking out loud and I said, well, I don't think X is small is going to work on this one. But then when I did it, it was actually X is small. So what you do is kind of dependent on how you're calculating things, right? If you're using the number solver on your 36X Pro or some other calculator, fast and easy, right? You just plug it in like it looks and it finds X for you. Beautiful. Why do we even need the X is small approximation? We don't, right? If you're using the quadratic equation, or you don't have a calculator that can do a number solver, you know, maybe you've just got the thing on your phone and no Wi-Fi, and so you're kind of stuck, that might be all you can do. So you can always try X is small. So this was my example of trying X is small. This would go to 0, and so X squared is this times this. The square root of that gave me this number. The check on X is small is we take this number and we divide it by whatever number we were adding or subtracting it to or from. It needs to be less than 5%. So this one was way larger, so X is small is not appropriate.
Wait, so sorry, for the percentage you're doing with what?
So if X is small, then X is 5% or less than what we're subtracting it from. Okay? So, you know, the big truck, big semi-truck full of peaches and one falls off. No big deal. Kid's got his little toy semi-truck, right? And it's got 6 peaches in it and one falls off. Okay, well, that's going to make a difference, right? So we can only use X is small when it is truly small, if that makes any sense. Does that help? And, you know, this is something that back in the day, you would have to use a quadratic equation to actually solve this. And this is just really tedious and annoying and easy to get wrong. And so, you know, this was a huge time saver. I don't know that we really need it anymore, but we're still teaching it. 2.72. Any other questions? Okay, so this is a similar problem, but kind of backwards. We've got a 0.175 molar weak acid solution. The pH is 3.25. Find Ka for the acid. They don't tell us what the acid is, so we can't look it up. So in chapter 16, we learned how to use initial concentrations and one equilibrium concentration to determine the equilibrium constant. So that's what we're going to do here. So here I kind of have to use HA because I don't know what it is. But there's my weak acid, and it's going to be in equilibrium with hydrogen ions and the conjugate base, whatever that is. And then we're going to make an ice table. ICE. So we can start in the same way that we did those previous problems, looking at initial concentrations. What's the initial concentration of the weak acid? It's a 0.175. It's the concentration they give us. And we say that the concentration of the hydrogen ions is approximately 0, and of the weak base is 0. But now, instead of doing minus x plus x, we're going to fill in one of the equilibrium concentrations. This is like what we did in lab last week, where we use a spectrophotometer to measure the concentration of the complex ion, and then we could calculate everything else. We can get the equilibrium concentration of the hydrogen ion from the pH, right? So pH is the negative log of the hydrogen ion concentration. But that equation is not so helpful because that's not what we're trying to find. We're trying to find the hydrogen ion concentration. So that's 10 to the negative pH, which would be 10 to the negative 3.25. Zero point zero 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 5623. How many sig figs should that have? In a pH, that's a logarithm. The numbers before the decimal point are not significant figures. So this has 2 sig figs, and so that would have 2 sig figs. I don't want to round it yet, though. That is my concentration at equilibrium. Okay? So then we're going to figure out what goes in the rest of these boxes. How do we get from 0 to this number?
Add that number.
Yeah, we add that number. So this change must have been plus 0.005623. Let's try that again. If that went up by that much, how much did this one go up by? The same. And since it started at 0, its equilibrium concentration is going to be the same. So what happened to the HA concentration? It goes down by that amount. So 0.175 minus 0.0005623. 0.174. Now this was subtracting, so that would be the last significant figure, but we just always want to write down 2 extras. So now we have the equilibrium concentrations. We can calculate Ka. So Ka is going to equal 0.0005623 squared, right? It's this times this. It's just that squared, divided by this guy over here, 0.17444. And my calculator is giving me more than 3 zeros, so I'm going to put it in scientific notation mode. 1.813 times 10 to the minus 6. If we're keeping track of sig figs, it comes out to be 2. In these calculations, it usually comes out to be 2 sig figs. But don't round everything in the middle to 2 sig figs because you get rounding errors, okay? So, just write down 4 digits. And you don't have to keep track of sig figs like this. You can just round it at the end. That's fine. Any questions?
This only works assuming that it's one hydrogen to acid, right?
Right. This only works if you have a monoprotic acid. So diprotic acids are actually not very common. And so when it's a diprotic acid or a triprotic acid, they'll tell you about it. And actually, it gets much more complicated when you have a diprotic acid, and we'll see that. Any other questions? The initial concentration and Ka of several weak acid solutions are listed. For which solution is the X is small approximation least likely to work in finding the pH? So X is small works when we're looking at the Ka and the initial concentration. Do we want Ka to be big or small for it to work? We want it to be small for it to work because then we know the ionization doesn't go very far. And do we want the initial concentration to be large or small in order for X is small to work? We want it to be large because then the number we're subtracting it from is less likely to be significant. So X is small likely to work is large concentration, small Ka. Well, this one is asking us the opposite, which is least likely. So then we're looking for the opposite of these. We're looking for a small concentration and a large Ka. So we can look at these guys. We're looking for a small concentration. Well, B and D are large concentrations. So those probably are not what we're looking for. And then we're looking at the Ka. Here's 10 to the minus 5 and 10 to the minus 3, which is least likely to work. C. I don't remember if I've put questions like that on exams before. Yeah, I just don't remember. Oh. Any questions about that one? Which solution is more acidic? That is, which one has the lowest pH? Yeah, I kind of gave the answer away. It is A. But we have two things to look at here. We have what is the acid and the concentration of the acid. So I would expect a fair number of people to pick C because the concentration is bigger. Like, oh, there's more acid in there, it's going to be a lower pH. right? But HF is a weak acid, HCl is a strong acid. So the strong acid is going to ionize completely. The weak acid only ionizes a little bit. It's not even halfway. It's just a little bit. Any questions about that? Remember, there's 6 strong acids, and you need to memorize them. Okay, the percent ionization of a weak acid. I just mentioned that weak acids, they don't even go halfway. So that would be 50%. So percent ionization is how we can measure how far does it go in a more meaningful way than the equilibrium constant. So percent is the part over the whole times 100. So here it's the part we're interested in, the hydrogen ion concentration, divided by the initial concentration of the acid, multiplied by 100. We want to know what percent of that weak acid ionizes. The part that ionizes is going to produce hydronium ions. And then this is the total amount. So we'll see that the percent ionization is relatively small for weak acids. Find the percent ionization of a 0.25 molar acetic acid solution at 25 degrees Celsius. Ka equals 1.8 times 10 to the minus 5. So percent ionization is the equilibrium concentration of hydronium ion divided by the initial concentration of the acid times 100. Do we have both of those values? No, we don't. We only have one of them. We have the initial concentration. How do we find the other one? Ice, baby. Gotta make another ice table. So here is, H, C2, H2O2. I'm just going to call it HA. And that's in equilibrium with H plus and A minus. You've been studying enough when you start dreaming about ice tables. Notice I said dream, not have nightmares. ICE. So the initial concentration of our acid is given 0.250. Initial concentrations of the products are 0. They don't tell us anything different. Here, we're not finding Ka, we're finding the hydrogen ion concentration. And so this is where we are going to use X's because we don't know how much it changes. So if we plug these things in, our Ka was 1.8 times 10 to the minus 5. And that's going to equal x squared divided by 0.250 minus x. We've done some problems with similar Kas and concentrations, and the x is small did work, so I'm gonna try using that here. So we're gonna say that is so small it's 0, and then x is the square root of Ka times the initial concentration. 0.002121. Before I finish the problem, I'm going to take this number and divide by the 0.25 and multiply by 100 just to check the percent. The percent here is less than 1%, so we're okay. So this is the hydrogen ion concentration. Now we can calculate the percent ionization. So percent ionization is the amount that ionized, which is this one, 0.002121, divided by the initial concentration of the acid times 100, 0.8485, 0.85%. Any questions? So only 0.85% of acetic acid ionizes. The other 99%-ish is intact acetic acid molecules. So it doesn't ionize very much at all. Yeah.
Is getting a percentage like that normal for a weak acid? Like, would it be much higher than we would do for a strong acid?
If we do it for a strong acid, it's essentially going to be 100. Yeah. But weak acids, it depends on their concentration. We'll see that in a minute. The concentration affects how much it ionizes in it. And then, of course, it depends on their Ka a great deal. But, yeah, they're small percentages. 0.85%. Okay, so the equilibrium hydronium ion concentration of a weak acid increases with increasing concentration of weak acid. But the percent ionization of a weak acid decreases as it gets more concentrated. So here we're looking at nitrous acid. A 0.2 molar solution is going to be 4.8% ionized. A 2.5 molar solution is going to be only 1.4% ionized. So the more concentrated the acid is, the less ionized it is. So the question here, why? So honestly, this is one of those things that I have had a little bit of a difficult time wrapping my head around. It's not something that I just remember from semester to semester. And so I don't expect you to remember it, right? If I can't remember it, I don't expect you to do so. If we decrease the concentration of HA, H plus also decreases, but it's not linear. It's not a linear decrease. And so they don't both decrease at the same amount. So, we've got a constant here. We've got x squared over y, basically. So when this increases, this also increases, but it's not a one-to-one, because this one's squared and that one's not. When it decreases, it's not a one-to-one. So lower concentrations are more ionized than high concentrations. So this one is asking us which weak acid solution has the greatest percent ionization. All the acids are the same. So here this is asked as a conceptual problem. On an exam, you could actually do the calculations and find out, right, if you can't remember which way it goes. We've got 0.1 molar, 0.5 molar, and 0.01. So it has to be either the biggest or the smallest, right? So we can get rid of this one in the middle. So do you remember from the previous slide, which way does it go? Lower concentration, is that more ionized or less ionized? It's more ionized. Lower concentration is more ionized. Higher concentration is less ionized. So this is going to be the answer. So just not using the KAs, but using the X's small approximation. Oops. So in this case, X is going to be the square root of Ka times 0.50. And here, X is going to be the square root of Ka times 0.0100. The percent ionization then is going to be the H divided by the concentration. I don't know if this is going to turn out to be helpful at all or not. We will find out. So that was just kind of a mess. Here we have the square root of 0.5 divided by 0.5. So that's the same as Ka divided by 0.5. And here we get Ka divided by 0.0100. So the percent ionization is related to the Ka. It's also related to the concentration. The higher the concentration, the smaller this value will be. So here 0.5, here 0.01. This is going to be a larger ionization. If you followed that, great. If you didn't, don't worry about it. I probably shouldn't have gone there in the first place. Any questions? Mixtures of acids. Now things are going to get interesting. So if you have a mixture of acids, calculating the pH can be complicated. But many times we can ignore the weak acid and just focus on the stronger acid. So here we're going to look at a strong acid and a weak acid, a mixture of 0.10 molar hydrochloric acid and 0.10 molar formic acid. There are three sources of hydrogen ions. There's the strong acid, the weak acid, and then the autoionization of water. When we were looking at weak acids, we said the autoionization of water, so small it almost never matters. Here, the strong acid versus the weak acid. What did we just see about ionization, percent ionization of weak acids? They're down around like 5%, right? It doesn't ionize very much. most of the time, this does not contribute enough to make it worth talking about. And then to make matters worse, the hydrogen ions from the strong acid actually reduce the formation of hydronium ion by the weak acid. So here are the three sources. We got our strong acid, goes all the way. We have our weak acid, and we have autoionization of water. Here, this K is super, super small. So this guy is putting out a whole bunch of hydronium ions. So when we do an ice table for that weak acid, the hydronium ion concentration is not starting at 0 because the strong acid was 0.1 molar, right? So we've got that from the strong acid, the initial concentration here. And so when we do this change, we find that the concentration, that X is small, and that adding X to 0.1 makes no difference at all. So many times we can ignore. Because here X ends up being 0.00018. You add that to 0.10, it's still 0.10. Any questions? So weak acid, strong acid, almost always you can just ignore the weak acid. That's nice. Okay, what about two weak acids? We can ignore the weaker acid and the water sometimes. So if the Ka's of those weak acids are significantly different, and here we're talking about differing by a factor of several hundred. So not like one is twice as big or 10 times as big, but maybe one is 1,000 times as big, right? Or 500 times as big. And if those concentrations are similar, or the stronger acid is greater. Okay, so let's look at this one. We have two weak acids. We've got one with a Ka in 10 to the minus 4, and the other with a Ka of 10 to the minus 8. Which is the stronger acid? Which Ka is larger? The 10 to the minus 4 is bigger, right? So HF is stronger than HClO. Does that make sense? What we're going to do is we're going to look at the strong acid first, and then we'll look at the weaker acid. Because this is asking us for the hypochlorite concentration, not the pH, the hypochlorite concentration. So we'll start with the stronger acid. And here I'm just going to abbreviate even more, because we know that all of this is aqueous. Do we really have to write the aqueous symbols in there? No, we don't. ICE. Initial concentrations. Well, 0.3 for the HF, and 0 and 0 for those products. Minus X plus X plus X, 0.3 minus X, X and X. So Ka is H plus times F minus divided by HF. Our Ka here is 6.9 times 10 to the minus 4. That's going to equal X squared divided by 0.3 minus X. You can use your solver. If you're good with math, you can do the X is small approximation without writing anything down. So for X is small, I get X is equal to 0.014. I compare that to the 0.3. Ooh, it's 4.795%. That's super close to 5. But it is less than 5. Zero point 0.01439. Did anybody do the solver and find out what X is? 0.046. So that's equal to the hydrogen ion concentration, right? So that is equal to the hydrogen ion concentration. That's the contribution from the stronger acid. Now we do another ice table for the weaker weak acid. HClO in equilibrium with H plus and ClO minus. Now, I could have all of this stuff printed up here, but then I would go too fast for you to actually write things down. And if you are writing things down, you're more likely to remember what we've done. So everybody should be writing stuff down. Okay, so initial concentrations for the HClO, that's its initial concentration right here, 0.100. What's the initial concentration of hydrogen ion? Yeah, it's this number. It's not 0 anymore because there's another acid present that's putting a whole bunch of hydrogen ions in there. So 0.001439, I'm just going to use the X is small. How about hypochlorite ion? What's its concentration? 0. So this one is 0. The reaction can only go to the right. So this is plus X, and this is plus X, and that's minus X. And so just following this pattern over here, our Ka is 2.9 times 10 to the minus 8. And that's going to equal 0.001439 minus X times X divided by 0.100 minus X. So this is a small number, a very small Ka, so let's try the approximation. We're going to say that that X is essentially 0 and this X is essentially 0. So then X is equal to this number times 0.1 and divided by that. 2.9, oops. 2.9 times 10 to the minus 8 times 0.1 divided by 0.00. And I'm going to express that in scientific notation. X is equal to 2.015 times 10 to the minus 6. Yeah.
For the hydrogen cation concentration,
Mhm.
put that number minus X, shouldn't it be plus X? Or
Oh, you're right. Thank you. Yes, it should. This one should be plus x. Thanks for catching that. So this should be plus x, and this one should be plus x. So how do I check if my x is small approximation was valid? I'm going to divide this by one of the numbers that was added to or subtracted from. Which one do I choose? I want to choose the one that's going to give me the largest percent. So I'm going to choose this smaller one. And that comes out to 0.14%. So 0.4% on my x is small check. Is x small? Yeah, x is small. Is x 0? No, x is not 0. So we did all of this, and at this point, it's common to forget what you were trying to find. What are we trying to find? We want the ClO minus concentration at equilibrium. Well, that's going to be this guy right down here, yeah? So that's going to be x. So this is the answer we were looking for. We just didn't recognize it right away. So the ClO minus concentration at equilibrium is going to be 2.0 times 10 to the minus 6. Yes?
Why is there an extra like 0 in front of the 0.01439? When we did, yeah.
It's supposed to be 10 to the minus 7.
Well, now you tell me about that. Okay, yes, I added a 0. Whoops, my eraser's way too big. .0. And we have to go fix it over here. And 2.9 times 10 to the minus 8 times 0.1 divided by 0.01439. And that ends up just changing the exponent here. And so that number divided by 0.01439 is even smaller. .015 times 10 minus 7 divided by 0.01439 times 100. So it's actually 0.0014%. So, thank you for catching that. Any other questions? It's a really small concentration. Because we were calculating the anion of the weaker acid, we had to do both ice tables to figure out what that was. If we were calculating the pH, would we need to do that? So these are different by a factor of about 10,000, really different. And these concentrations are similar, so those guidelines say we probably don't have to. Now that we did it, let's look and see, well, how much did the weaker acid contribute? Well, it contributed this much. I'm sorry, that's from the stronger acid. it contributed the X here. If I add X onto that number, it doesn't make any difference. So the pH is going to be the same, but if I calculate the anion here of the weaker acid, I have to do 2 ice tables. Which solution is most acidic? Lowest pH. Well, what are we looking at here? Is HCl strong or weak? Strong. How about HF? Weak. HF is still weak. How about HClO? Also weak. Right? HCl is strong, but HClO is weak. So here we have, this is 2 molar in a weak acid. This is 2 molar in combined weak acids, and this is 1 molar in a strong acid. Which one's going to be more acidic? The strong acid. Because when those weak acids ionize, they only ionize a little bit. So the fact that the concentration is twice as big doesn't matter.